Okay, now that we've talked about the idea of correlation, looking for linear or monotonic association, I want to take the next step and start talking about the idea of simple linear regression. Now, the primary use for linear regression is in fact prediction. It's building a mathematical model that we can use for predictive purposes. Simple linear regression is called simple because it involves only one predictor variable, such as the pollution index that we studied and the number of dead fish, or the idea of the number of, or the amount of sugar and the number of cavities. Pollution was used to predict dead fish. Cavities could be used to predict the number of, sugar. The amount of sugar could be used to predict the number of cavities. So linear regression is a technique we use to model linear data with a linear model. In other words, the equation of a line. That's exactly what we're doing. Remember in algebra, the equation y equals mx plus b? Well, that's exactly what we're going to be using with a slight twist on it. But this is exactly the idea that we will be concentrating on. Now, the process that we use is actually referred to as least squares. Least squares regression. Now, the reason it's called least squares is, here's the idea. I'm going to draw, for sake of conversation or for illustrative purposes, 3 points. Now, we never do correlation, I wouldn't think, or excuse me, or regression with only 3 data points, but this serves very well for instructive purposes. Now, here's the idea. If we see a linear trend, we're going to fit this with a line. We will then use the values on the line as estimated values for the vertical variable, or the y variable. Now, least squares, what happens is this value right here has a coordinate x and y. Right, this is an actual data value that was observed. Now on the line, that's going to have coordinates x, and I'm going to use y hat. Y hat signifying it was a predicted value. So we use values on the line as predicted values for y. Now clearly, if this is a true value of y, and we predict it down here, then we have an error. And I'm going to call this E. Now we have E and epsilon. Epsilon is for population data, if this was actual true population, and E is used as a statistic for sample data. So here's the idea. If I were to draw these 3 points here in a piece of paper and give it to 20 different people and say, fit a line through here, fit a line through it that you think best fits this data, I'll probably get 20 different lines. So what least squares does, it says, all right, the values above, when the actual value is above the line, if I subtract y minus y hat, that gives me a positive value of E. Now, for values below, y minus y hat will give me, I should put equals there, a negative value for E. So this would also, this distance here, the error would also be negative, some negative value for E. Now the idea is I can take this line, change the slope, and the y-intercept, move it up or down, wherever I need to, such that if I add up, oops, let me do that one again. If I add up I equals 1 to n of all the errors equals 0. I can adjust that line such that those distances, the positive and negative distances, will cancel each other out. Now, where have you heard that before? Think about this. This is the exact same thing that the average did. If I have a data set and I calculate the average, then take every data value, subtract from it the average. Those data values below the average would be negative. Those data values above the average would be positive. If you add up all those distances, you get 0 every time. So the least squares regression line is really like an average. It's like an average to bivariate data, just as x bar, or mu, is an average to univariate data. It's the same sort of a concept. Okay, so that's basically the idea behind least squares regression. It takes these errors and it finds a slope and intercept for this line, kind of moves it around in a mathematical sort of way. It's not really moving it around, but in a mathematical sort of a way, with a constraint that all the errors must add up to 0, and that will determine this line uniquely for any given data set. Now, the equation for the population regression line. The population regression line is going to have population parameters in it. First of all, y is a specific value of y, or actually, y is like the equation of the line, I'm sorry. If this is my data, if this is population data, then y equals beta naught plus beta 1x is the equation of this line. Now, we're thinking of beta 1 as the same as m. Remember the equation y equals mx plus b? In statistics, we can turn those around. And the reason we do that is because if we have more than one predictor, there could be an x1, an x2, and x3 different variables that I use to predict y. If there's more than one of them, then we just keep going. Would be beta 2, x2, beta 3, x3, and so forth. Now, in this class, we're going to stick to simple linear regression, which is only one predictor. So there's only going to be one variable that we're labeling as x. Now, a specific value yi, like this guy right here, for a population can be represented as beta naught, the y-intercept, which is like right there, plus beta 1, x1, that's the slope of the line times a specific value of x, plus epsilon I. Epsilon I is the error. Now, the assumptions that we're going to be working with, the vast majority of them are really centered around the distribution of these errors. Because if we know the distribution of the errors, then we can model them. And that will allow us to produce a reliable or usable regression equation. Now, for the sample regression equation, we have the exact same idea, only we see the equation of the line y equals b0 plus b1x. And any particular yi is b0 plus b1 xi plus the error ei. Now, just like we've been doing all semester long, we use sample statistics to infer about population parameters. So we will use the EIs to make a reference about the epsilon I. So the distribution of the sample errors, we will use that to make inferences about the distribution of the population errors. Now, the assumptions. The first assumption is that the data, actually I shouldn't say data, we should say population, that the population has a bivariate normal distribution. Now in reality, this is extremely difficult to actually do. So what we have found as a good rule of thumb is if we do a scatter plot, and what we see in the scatter plot is something that looks like it has a linear trend, then this idea of bivariate normality is reasonably satisfied. If the scatter plot has a linear trend to it. So if you see something that's curved, something that you'd use Spearman's on, right now it's all over. You wouldn't do any type of regression on it because we're sticking to the idea of simple linear regression. Okay, the next assumption is that the error term epsilon is a random variable that is distributed normally with a mean of 0 and a constant variance. So we need to be normal, the mean of 0, and the constant variance. Now for normality, I'm going to label this as 1, 2, and 3. 3 different things we need to address. For the normality, it's satisfied by a normal plot of the error terms. And these error terms are also referred to as residuals. That's important because your calculator will actually calculate the residuals and save it in a list for you that it calls resid. So all we got to do is a normal plot just like we do any other normal plot, but specifically look at the residuals. Are the residuals reasonably normal or not? All right, the next one, a mean of 0. That's a done deal. This is satisfied. Whoops. By the least squares, I'm just going to say process. Okay, the mere fact we did least squares regression, one of the restrictions for least squares regression is that the sum of the errors is 0. That's how it actually finds a slope in the intercept for the regression equation for the line itself. And the third one is the constant variance. That is satisfied by a scatter plot of the x data, whatever your independent variable is, whatever you're using to predict with, by the residuals. So I'll have my x data on the x-axis and the residuals on the y-axis. Now the other assumption that I actually didn't put on here that I really need to talk about is these epsilons must also be independent. And that is also addressed by this exact same scatter plot. And I'll do some, and we'll take a look at it and show you how this appears to be independent, or how by looking at the scatter plot you know it's independent versus how it looks if it's dependent. And likewise for the constant variance. We'll take a look at an example and actually show you what that's all about. Oh, there it is, independent. I had it on the next page. Sorry about that, I forgot. So again, that's satisfied by the exact same way. Now, I'm going to draw a couple of scatter plots to address the independence and the constant variance. So, if this is the x-axis, what I'm looking for in the x versus my residuals is basically a cloud. Something like that. And what I'm seeing is two things. Number one, I'm seeing vertically, essentially, same distance. That's the variability. Remember, this guy up here, this had a positive residual. It was the value on the y-axis here, it was this distance from the regression line. A negative value was this distance below the regression line. And what we're looking for is a line such that the data above and below is kind of evenly scattered. And that's what this would show. Now, on the other hand, if we had something that kind of fanned out like this, and then maybe came back together, it may or may not come back together. Coming back together is not a requirement. See what's happening here is as I'm moving along, the variability is changing. See, I have this fanning out and then this fanning in sort of a thing. Okay, that's bad. This is a violation of the constant variance assumption. Now, in terms of the independence, on the same residual plot, if I see residuals that perhaps look like this, this shows that it's not independent, because what's happening is there's a clear pattern. The fact that I have low values down here indicates I'm going to end up with higher values and then come back down into the lower values. This is not independent. Matter of fact, if I see this type of curvature, what really happened in my original data, even though I may not have seen it, what's really happened is that my data, I'm going to exaggerate a little bit, my data actually had curvature to it. Because if I fit a line to it, these residuals would be negative, these residuals would be negative, and these residuals would be positive. See, negative, positive, negative, negative, positive, negative. There's curvature in the data, and I didn't see it. Or you didn't see it when you actually did the original scatter plots. That's what's going to result in this type of residual plot. Now, if the residual plot looked like the constant variance one, you see there's no pattern in it, then you're good to go. So that's how we're going to actually address the assumptions. And in the next video, we're going to do an example, take some data, walk all the way through the process, addressing each of these assumptions step by step.